Yeah, welcome to the lectures in chemistry and the topic on atomic structure and chemical bonding. My name is Mangala Sundar and I am in the Department of Chemistry as a professor in the Indian Institute of Technology, Madras, Chennai. My email addresses are given here for you to correspond or for you to request additional information. This is the first of a number of lectures on solutions to a few important differential equations. Okay. So the lecture title is Power Series Method. There will be several lectures on this, and this is important for students who would like to understand the mathematics behind and also the solutions behind the problems that we have discussed so far, the harmonic oscillator, the hydrogen atom, and even particle in the box, where the solutions appear to be simple enough for you to write down. But there is a general method, and the power series method is something that is very well known in the mathematics of the solution of differential equations, second order and partial differential equations. But I shall illustrate what is minimally required for us to understand the method, and will not worry so much about the convergence of the solutions, the uniqueness of these solutions and so on. That is obviously the second level reading if you are interested in the more abstract mathematical nature of the solutions. Here we are trying to handle the practical problems and try to appreciate why the solutions are the way they are. We will start with the two elementary differential equations for which you already know the solution, but the method of power series will also be shown to tell you how such methods work for the more complicated equations. The purpose of this series of lectures is to follow up with the three equations that you have already encountered, namely the Hermite differential equation for the harmonic oscillator. The second one is the Legendre differential equation, which you have seen now in the form of the solutions to the angular part of the hydrogen atom, namely the spherical harmonics. Legendre and associated Legendre polynomials. And the third equation is the Laguerre equation. The Laguerre equation is the one that you saw as giving you the solutions to the radial part of the hydrogen atom. Therefore, this whole week or whatever period that the next few lectures will contain some details of the mathematics. Let's start with the first simple equation, not even second order, but we'll start with the first order. All of you know that the differential equation dy by dx minus ky is equal to 0 has the solution y of x, which is a function, y is a function of x, as some constant a times e to the kx. Okay? Because that is immediate, because then you know dy by dx gives you k a e to the kx, which is ky, and therefore this is that equation. Okay? Now let us illustrate the power series method for this differential equation to begin with. So let me propose a solution for y of x as an infinite series containing all the terms starting from n equal to 0 to infinity, starting from n equal to 0 and going up to infinity, a n x raised to n. This is a short representation for the term a naught plus a1 x plus a2 x square plus etc. plus a n x raised to n plus and so on. It is in an infinite series. Now let us try and understand this method using this particular form of the solution. Okay. We propose this as a solution and then determine the constants if we can. Okay. Dy by dx, if I take the derivative of this expression, okay, then you know a naught goes away and a1 is the first term that is non-zero. Then you have 2 a2x plus you have 3 a3x square plus and so on, and the term that you see here as a general term gives you n a n x raised to n minus 1 plus so on. and this can be written in the form of a summation as n equal to 1 to infinity n a n x raised to n minus 1. You can also see that from here. Okay. Since n equal to 0 does not contain any powers of x, the derivative of this term will get rid of the a 0, but every other term will have n a n and will have x raised to n minus 1, and that is what I have written here. Now, the differential equation that you are trying to solve is dy by dx minus ky is equal to 0, and therefore, let us write this as a naught plus a 1 x plus a 2 x square plus a n x raised to n plus and so on. This is the ky term multiplied by ky. So, let me write this as ky minus dy by dx is equal to 0, and then subtract the derivative, namely minus a 1 dx is gone plus 2 a 2 x plus 3 a 3 x squared plus etc. And the nth order term, if you have to write in here, you will have to write this as n a n x raised to n minus 1 plus n plus 1 a n plus 1 x raised to n plus and so on. So, the general term, if you look at it, is if we arrange them in the order of coefficients of various powers of x, if we write down the coefficient of various powers of x, x raised to 0, that is constant. If you look at the constant, it is k a naught on the first this one, and then minus a 1 is equal to 0, or a 1 is equal to k a naught. What is the next term that you see? What you see is 2 a 2 power of x is 2 a 2 plus k minus k a 1 is equal to 0, k a 1, yes, this is the x raised to 1 power. The coefficient has this relation. Therefore, what you have is a 2 is equal to k a 1 by 2, and a 1 is already there as k a naught. So, you have k square a naught by 2. So, you have a 2, and the third, if you write the x raised to 2x square, then the term is 3 a 3 minus k a 2 is equal to 0, k a 2 is equal to 0. Okay. Therefore, you have a 3 is equal to k a 2 by 3, which gives you k a 2 is already given by that. Therefore, it gives you k cube a naught by 3 factorial. Remember, now all the constants are expressed in terms of one undetermined constant a naught, okay. And that is what you should expect anyway, because this is a first order differential equation. Therefore, the general solution has only one undetermined constant, and now that constant turns out to be the a naught. So, what is the general term for this? The general term, if you do a n following this, it will be k raised to n by n factorial a naught and so on. Therefore, now you have found the solution for the differential equation, namely y is equal to sum over n equal to 0 to infinity a n x raised to n is given by a naught plus a naught x plus kx plus a naught k square by 2 factorial x square plus a naught k cube by 3 factorial x cube and so on. Here, look at all these answers. Okay. A 3 is k cube by 3 factorial a naught, a 2 is k square by 2 factorial a naught, a 1 is k a naught, and a naught is a naught, of course. So, what you have is essentially a naught into 1 plus kx plus k square x square by 2 factorial plus k cube x cube by 3 factorial plus and so on plus k raised to n, kn x raised to n by n factorial. See, this is nothing but the exponential kx. This is the power series for exponential kx. Okay, power series. Therefore, you see y is equal to a naught e to the kx, where there is one constant undetermined, is the solution to the differential equation dy by dx minus ky is equal to 0. Okay. So, this is very elementary, so it is easy to see, and we have not touched the question of whether this exponential, the representation and the power series representation, whether the power series converges and so on. You know that the exponential kx keeps on increasing as x increases and is unbounded as x becomes infinite, and so does the power series. So, therefore, there are questions about the convergence, questions about the uniqueness question we will not discuss. In this case, of course, it is easy to show that this is a unique solution, and this is one way of looking at this. The reason for doing this is that one more equation and this will give you the general process by which the three equations I indicated earlier, the Hermite's equation, the Legendre equation and the Laguerre equation, how they are solved using the relations. Now, what I did not specify to you is what is known as a recurrence relation in the whole process. So, let me just indicate that. The recurrence relation is essentially the coefficient a n plus 1, how is it connected to the previous coefficient a n. Okay. Now, if you look at that, the coefficient a n plus 1 is connected to the coefficient k a n by this relation k by n plus 1. Okay. Now, you can see that when n is 0, this is k times a1, this is a1, and therefore it is k times a naught. When n is 2, it is k by 3 a2, this is a3, this will be a2. So, the recurrence relation tells you the relation between the coefficients in some form such that they can be generalized, and the result that you saw here, namely this result a n is equal to k raised to n factorial, is a repeated substitution of this into a by a n minus 1 and then a n minus 1 by a n minus 2 and a n minus 2 by a n minus 3 and so on. So, finally, you get to this. Okay. So, this is the recurrence relation, and this is the final coefficient that is determined in terms of the undetermined coefficient. Okay. Now, another equation for which you also know the solution, we will discuss that. This is d squared y by dx squared minus omega squared y is equal to 0. Second order differential equation, and all of you know the solution from the particle in a box for this, that let us write plus y square. That is the one that you have been dealing with. Of course, minus y square will give you exactly the same relation that you already had. So, for d square y plus omega square y, we will do that, and you know that the solution of y of x is a cos omega x plus b sin omega x. And for a particle in the ring, you were using this solution, y is equal to a e to the plus I omega x plus b e to the minus I omega x. They are both equivalent anyway. Okay. Because if you expand the exponential using cos and sine and cos and sine, I will write this by a different constants a prime and b prime. Okay. And you can relate these constants to each other. The general power series method is something that we should look at for this problem, and this will make you familiar with the remaining parts of the lectures on this topic. Now, the differential equation that we have to solve is d square y by dx square plus omega square y. So, let me just go back and what I have written. So, if you take the second derivative is the expression that I am just copying here. So, d square y by dx square is given by this term. Let me highlight all of that. is given by this term, okay, all these things. This is an infinite series, and then the differential term, namely the omega square y is this term omega square a naught a1x a2x, all these. This is the omega square term. So this is the omega square term, and this is the d square y. Then you collect the powers of the individual x's, namely x raised to 0, which is a constant, and if you look at that, you see it is 2.1 times a2 plus omega square a naught, that is 0. The coefficient of x is 3.2 times a3 here, this term, and the corresponding the omega square term for the power of x is this term omega square times a1, and then you can write down a few more terms, namely 4 times 3 a4 plus omega square a2 is 0, 5 times 3 a5 plus omega square a3 and equal to 0. So you see that there are two independent sequences of relations. One sequence involves a naught and then to a2. The next, that sequence contains a2 to a4 and the things that I have not written down, a4 to a6, a6 to a8 and so on. So that involves only the even indices. The other sequence is the one which is marked in green here. It involves a1 and the relation between a1 and a3, and then the relation between a3 and a5, and then between a5 and a7. So you can see that the odd indexed coefficient a1, a3, a5, they are all connected to a1. The even indexed coefficient are all connected to a naught. That is not surprising that we have only two undetermined coefficients, because it is a second order differential equation. It requires two conditions to be fulfilled, and for the particle in the box, if you recall, you did that for the box at one point psi of x is equal to 0 and psi of x is equal to L 0. You put that in those two conditions. They determine with the other boundary condition, they determine both the a and b. Therefore, we need two undetermined coefficients and everything else can be written in terms of them. So let me write therefore the general relation between these coefficients. Okay. The general relation is a to n, that is even index. A to n is minus 1 raised to n omega to the 2n divided by 2n factorial a 0. A 2n plus 1 is minus 1 n plus 1 omega to the 2n plus 1 divided by 2n plus 1 factorial a1 by omega. Okay. Quickly, what does this mean? If n is 1, a2 is minus 1 raised to n, so it is minus omega 2n is omega square, 2n factorial is 2, a naught. Okay. Now you see the relationship between a2 and a naught. A2 is minus omega square by 2 a naught, no problem, and a4 is minus omega square divided by 4 here, this one. A4 is minus omega square a2 divided by 4 into 3, 4 times 3, and a2 is already a minus, therefore it is plus omega raised to 4. A2 also contains an omega square and it is a naught divided by 4, 3, 2, 1, so it is 4 factorial. So a4 is 4 factorial omega 4 a naught. So it is easy to see that this generality is here, that a2n is minus 1 raised to n, a4 is plus a2, a6 will be minus a6 and so on. You can see that. Therefore, this is the recurrence relation between the coefficients in the even n, and this is the recurrence relation likewise between the coefficients in the odd indexed n. Now, n is equal to 1, 2, 3, etc. Okay. Remember the power series for cosine omega x. Cosine omega x is 1 minus omega square x square by 2 factorial plus omega 4 x raised to 4 by 4 factorial minus and so on. And the power series for sin omega x is omega x minus omega x whole cube divided by 3 factorial plus omega 5 x raised to 5 by 5 factorial minus and so on. You will see that these two coefficients basically lead to exactly those power series starting from A0, A2, A4, A6 etc. They all correspond to the cosine power series, and the series A1, A3, A5, A7 etc. they all correspond to the coefficients of the sine series, okay, with the fact that it is A1 by omega which is needed, because otherwise it will become omega raised to 2n. So, this omega is a constant anyway. So, we have redefined the constant, and this is the cosine series. So, now you can therefore write the final solution as the following, namely y of x is equal to a cos omega x plus a here is our a naught, okay, a naught, and then you have a1 by omega sine omega x, which is the same as what you had earlier written, a cos omega x plus b sine omega x. Okay. So, the power series method is something that is the underlying the algebraic tool through which one obtains solutions for complicated differential equations, and the power series method is very well known for a special class of differential equations leading to what are known as special functions. And some of the examples of these special functions that you will see in physics and mathematics and also sometimes in chemistry are Bessel functions. The differential equation is called the Bessel differential equation, Legendre functions and the associated Legendre polynomials. Coupled with the phi part, they are called the spherical harmonics. Legendre functions, these are called the polynomials. They are all various powers. We will see one of them, and then we have the Hermite polynomials or Hermite functions, and then Laguerre functions, or Laguerre polynomials, and then there are others like the Chebyshev. It's often written in many different ways. Chebyshev C. Sometimes people put a T in front of this too. Chebyshev, Russian mathematician, Chebyshev polynomials and so on. Therefore, the differential equation method, the solution of which using the power series, is something that has been well established, and the physicists like Schrodinger and many others had earlier studied the differential equations, and they saw that the mathematics of the hydrogen atom and the mathematics of some of the atomic and the molecular chemistry problems go back to the polynomials and the methods which were discussed in mathematics independently of quantum mechanics, and therefore they bridge the gap between the known mathematical results and the unknown, the new problem of the quantum mechanics or the problem of quantum mechanics. And so you can see that the fusion between the two is a very, very well studied mathematical technique. We will see a few examples as part of this course, and we will see more of it in the Hermite polynomial in the next lecture. Until then, thank you very much.